We are going to begin factoring polynomial functions. You've already learned how to factor polynomial functions that are quadratics. However, we are going to be taking a look at functions that have higher powers. I'd like to start off with a warm-up. It says to determine whether the given binomial is a factor of the polynomial px. If I'm trying to determine whether or not something is a factor, we're going to use synthetic division. And the way that we know if it's a factor or not is if the remainder equals 0. Starting with A, if I'd like to use synthetic division, remember it has that L shape. And in the first row, I'm going to put the coefficients of the function. Remember, it must be in standard form with placeholders if necessary. Looking here, I have an x squared term, an x to the first power, and a constant. So I don't have to rewrite it, and I don't have to put any placeholders. To get the number that goes on the outside, we need to set the divisor equal to 0. By doing that, I'd add 3 to each side, so I'd have x equals a positive 3. Once we have it set up, you would need to bring down that first coefficient and start your pattern of multiplying, adding, multiplying, adding. So 1 times 3 is 3, 2 plus 3 is 5, 5 times 3 is 15, 15 and negative 3 added together would give me a 12. So 12 is my remainder. If the question is whether or not this would be a factor, the answer is no, because the remainder was not 0. Let's take a look at part B. Once again, I need to use synthetic division to set it up. I need to make sure that this is written in standard form with placeholders. So I see that I have an x to the fourth, x cubed, and then it jumps to an x. So I am missing an x squared, and I have 0 of them. So I'm going to put plus 0x squared in between the x cubed and the x, meaning my coefficients are 2, 8, 0, 2, 8. To get the number that goes on the outside, I need to set my divisor equal to 0. I would subtract 4 from each side, giving me a negative 4. Bring down that 2. Let's multiply, add, multiply, add. So 2 times negative 4 is a negative 8. 8 plus negative 8 is 0. 0 times negative 4 is 0. Add those, it's 0. 0 times negative 4 is 0. 2 plus 0 is 2. 2 times negative 4 is negative 8. And then 0 is my remainder. So is this a factor? Yes, it is. I'd like you to pause the video and try 1A and 1A had a remainder of 25, so the answer was no. 1B, you had to remember to set the divisor equal to 0, and when you solved, you would get a 2, meaning 2 would be the outside number here. Once you perform synthetic division, we would end up with a remainder of 0. So yes, it was a factor. We are now going to do a review of factoring quadratic functions. Since this pertains to what we will be learning in your Chapter 3, Section 4. Remember, when we are factoring, you should always check for a GCF first. And if there is one, we would pull that out. Starting with number 1, if I look at each of my terms, there is no greatest common factor, so I don't have to worry about that. There are 3 terms here, and A is 1. So you might recall a method that I called guess and check, which is where we look at the factors of the last term and ask ourselves what we could use to get the middle term. So the factors of 15 are 1 and 15 and 3 and 5. Because this is a negative 15, I know that one of them will be a positive number and the other will be a negative. If I ask myself which of the factors could get me to the negative 2, well, that would be the 3 and the 5. The 3 must be positive and the 5 must be negative if I would like to get a negative 2. Meaning the factored form is x plus 3, x minus 5. Taking a look at number 2, there is a greatest common factor. Remember, we're always checking for that first. So there is a GCF of negative 3 for the constants, because you can see each term is divisible by a 3, and it's negative because we always want that first term to be positive. So that's why I'm pulling out that negative there. And also, if I look at the x's, all 3 terms contain an x, so I can pull out an x to the power of the lowest degree. So I could pull up to an x squared. Negative 3x squared doesn't magically disappear. We must write it out front, and inside of parentheses we would write what remains. Remember, to get what remains, we would divide each and every term by that negative 3x squared. So dividing each term by that negative 3x squared, negative 3 divided by negative 3 is a positive 1. X to the 4th over x squared, we would subtract the powers, so 4 minus 2 is 2. I have 1x squared, or just x squared. Positive 30 divided by negative 3 is a negative 10. X cubed divided by x squared is x to the 1st power. A negative 75 divided by a negative 3 is a positive 25. And then x squared over x squared becomes 1, or they essentially canceled each other out. Now that I've pulled out a GCF, I can see that a is 1 here, and the factors of 25 are 1 and 25. 5 and 5. We always want to ask ourselves if we can factor further. So that's what I'm doing here. I've already factored pulling out a GCF, so now I'm seeing if I can factor this one. So do any of these pairs using the same signs, because it's positive, give me a negative 10x? Well, yes. If we use the 5 and the 5 using same signs, both would have to be negative in order to give me that negative 10. So I have negative 3x squared times x minus 5 times x minus 5. We could simplify further. Remember, something times itself can be rewritten as something squared. So the final answer is negative 3x squared times x minus 5 being squared. You may not have realized it, but we used a rule called, let me get out a different colored pen here. Number 2 is a perfect square trinomial. If you go back and watch the factoring videos, you'll see the exact rules written out. I also took the time to really quickly write down the rules here. Like I said, you can go back and watch the factoring videos to see examples worked out. Number 3. Now this is a binomial. Whenever we have a binomial, the first thing we should do is check and see if it could be a difference of 2 squares. I went ahead and wrote down the rule here as well if you'd like to pause it and write it down. Again, you can go back and watch the factoring videos to see more examples worked out. But coming back to number 3, I want to see, is this a difference of 2 squares? Meaning, can I identify something squared that would give me the first term? And can I identify something squared that would give me the second term? That would be our A and B terms. So starting with this first term here, can something squared give me 16x squared? The answer is yes. 4 squared would give me 16, and x squared would give me that x squared. I am subtracting, so I do know it is a difference, and then something squared does give me 81. That would be 9. So then I would just plug it into that rule, which is stating that a squared minus b squared is equivalent to a plus b times a minus b. We always want to check and see, can we factor further? So can I factor the 4x plus 9 or the 4x minus 9 any further? The answer is no. So I'm ready to move on to the next one. Number 4, once again, I want to check and see, can I use the difference of two squares here? It does look like the first term, x squared, could give me x squared, and the second term, 3 squared, would give me the 9. So they are two perfect squares here. However, I cannot use the difference of two squares here because of that plus sign. This is not a difference, it is a sum, which means it is not factorable. The problem is I won't have those different signs to cancel out to get a middle term of 0x, because remember, this is technically equivalent to this. I have to use same signs. I can't use the same signs and get to that 0. Taking a look at number 5, switching back to my green pen. The first thing we should always do is check for a GCF, and I do see that there is a GCF here of not a constant, so no number other than 1. However, I could pull out a variable of x squared. Remember, we always want to pull out the lowest power. If I pull out an x squared, I need to account for it. It doesn't magically disappear, so x squared goes on the outside, and in parentheses, I would write what remains. Divide each term by x squared. I would get 8x minus x squared over x squared simplifies to 1. Again, it doesn't magically disappear. We need to account for that. Check and see if we can factor any further, and I cannot factor 8x minus 1 any further. Number 6 is another trinomial. So I'm going to go ahead and do guess and check, because I see a is equivalent to 1. That's the fastest method. So I'm going to list out the factors of 20, 1 and 20, 2 and 10, 4 and 5. Because the 20 is positive, we must use same signs, and I need to ask myself, using same signs, can I get to a negative 9? Well, the answer is yes, and both the 4 and 5 would have to be negative in order to give me a negative 9, meaning it's x minus 4 times x minus 5. I cannot factor that any further. Same thing for number 7. It's a trinomial where a is 1, so I just look at the factors of positive 16, so that's 1 and 16, 2 and 8, 4 and 4. Using same signs, is there any way I can get to a negative 8? The answer is yes. I would just have to be sure both of them were negative 4s. So I have x minus 4 times x minus 4, or that is x minus 4 being squared. Notice how I used guess and check here, but I could have also used a perfect square trinomial, because a would be x and b would be 4, and the middle term should be 2 times a times b. 2 times x times 4 does give me 8x. Because it's minus plus, so minus plus, I know it's going to be a minus b squared. So x minus 4 being squared. Please watch part 2 in order to finish the notes.